Welcome, ladies and gentlemen. Good morning. May I have your attention, please? Thank you. Okay, so let's go ahead and sketch a graph of our parametrically defined curves, and we can do so by creating a table of values, just like we first graphed back in pre-algebra. Right? It's just that our table of values won't just be an x, y chart; it'll be a t, x, y chart. And on our time interval, we can then tell at what points x, y on our Cartesian coordinate plane the point is, right, based on the time value we are 0 to 4. So this is interval 0 to 4 is time interval 0 to 4. Let's see where the particle is at each of these time values. So I'll go ahead and construct an XY chart, but it'll include my parameter t. All right, so at time t equals 0, at what x coordinate, right, is the particle? Well, it's at 0 minus 2 is negative 2. At t equals 0, the y coordinate is 0. So I start the problem at t equals 0, and the point is negative 2 comma 0. That's pretty sweet. Not so bad. At time t equals 1, the x coordinate is 1 minus 2 is negative 1. The square root of 1 is 1, so I'm at negative 1, 1. At the time value t equals 1. Then go gadget arm. I'll go ahead and choose then 2, 3, and 4. And you guys get the scheme. We can see exactly where the particle is as time progresses from 0 through 4 in my interval. So 2 minus 2 is 0. And the square root of 2 is the square root of 2. That's about 1.414. So 0 comma 1.414. Very nice. 3 minus 2 is 1. The square root of 3 is the y coordinate, right? That's about 1.7. There. And at t equals 4, 4 minus 2 is 2. Square root of 4 is 2. So it looks like we're at 2, 2. All right. Ain't nothing to it but to do it. We'll go ahead and show the direction of motion there as we move from t equals 0 to t equals 4. And we could show that with a couple little arrows indicating the direction of motion. And no, you can't trick me into saying Oreos again. Oh, it does sound kind of good any time of day. All right, raise your hand if you have that picture for the first part. Great, now let's relate x and y directly and eliminate the parameter. How do we do that? Well, typically we can solve one of the equations for t and then substitute it back into the other one. Does it matter which? No, but sometimes one method might be easier than another. So it looks like I'll go ahead and rearrange that first equation, x equals t minus 2. If x equals t minus 2, then t must equal what, Riley? X plus 2, I'm down, and then we'll go ahead and substitute that into my other equation, y equals, so I get y equals the square root of x plus 2. And by golly, doesn't that look, right, like this portion of the graph? Looks like the square root of x plus 2 shifted 2 to the left. Awesome. Raise your hand if you had this relation for number 1. Yes! Way to go. What question do you guys have about number 1? Okay. Then let's take a look at number 2. In this case, we've got some trigonometric equations for my x and y coordinate. And again, our scheme will be the same. On 0 to 2 pi, we'll go ahead and construct a t, x, y chart. And we'll choose convenient time values from 0 to 2 pi. It looks like sine and cosine. So if I choose 0, we could do, well, let's go pi over 2 for now and see if we need more. Pi, 3 pi over 2, and 2 pi. We'll see if that's enough. So at at t equals 0 rather, the cosine is 1 times the 2 out front is 2, is that right? At t equals 0, sine of 0 is 0. So it looks like we start out at time t equals 0 at the x comma y point of 2 comma 0. At pi over 2, cosine is 0. Sine is 1 times 3 is 3. So it looks like we've gone to 0, 3. At time t equals pi, cosine of pi is negative 1 times 2 is negative 2, 0, and we see the pattern now. Zeros at my pi over 2 multiples for cosine, the x-coordinate, and 1 times 3 is 3, but negative, right? At 3 pi over 2, sine is negative 1 times 3, good. So then we're negative 2 comma 0, 0 comma negative 3, and lastly, at 2 pi, that's not so good. At 2 pi, cosine is back to 1 times 2 is 2. Yes, the arm motions are necessary, and 0. So we're back to 2 comma 0. Oh, yeah. Okay, so let's make our picture. Well, gosh, that looks like a parametrically defined ellipse, doesn't it? Right? It's not a circle. It looks like my major axis, my vertical axis is stretched by a factor of 3. My horizontal is stretched by a factor of 2 from the basic unit circle, but it's an ellipse. So there we go. Oh, Nelly! And our direction of motion as we go around the horn. And it looks like in the 0 to 2 pi, we trace out 1 full rotation of the ellipse. Awesome. Raise your hand if you have this picture for number 2. Yes? All right. Now let's go ahead and relate x and y directly. In order to do that, when we have our trigonometric equations, we want to rely on our Pythagorean identity. Cosine squared t plus sine squared t equals 1. And so we'll go back to our Pythagorean identity. We know that so cosine squared t plus sine squared t equals 1. And if x equals 2 cosine t, then cosine of t must equal x over 2. So it looks like cosine of t equals x over 2, and sine of t equals y over 3. Is that right? So through direct substitution, we can rewrite cosine of t quantity squared as x over 2 quantity squared. And we can write sine of t quantity squared as y over 3 quantity squared, and then that's equal to 1. When rewriting in standard form, we can see visually that my horizontal, my minor axis is 2, and my major axis, in this case, because that's larger, right, my vertical axis is 3, and we can see that. So here we've got our standard form for ellipse, and we can compare that now with our parametrically defined curve with sine and cosine. Awesome. Raise your hand if you had the Cartesian relation. Yeah, no? Okay, so do you see how to do it now? We can start with Pythagorean, and that was way back from our prerequisite unit back to start the year. We'll box this bad boy, and I should probably do the same over here. PDF full, Tyler. PDF full, maybe. Great. Okay, we'll go ahead and pause it here. We're going to take care of a double check. Not Aaron Rodgers discount double check, but a review followed by OTL number 0. Thank you, ladies and gentlemen. Today, we're now going to apply our differentiation to parametrically defined curves. And so if x and y are both differentiable functions of t, then guess what? We can still find the slope of the curve in the Cartesian plane, right? The xy coordinate plane, dy dx, the rate of change in y with respect to x. It's just that we'll differentiate each portion, our x equals and our y equals parametrically defined equation, separately and write as a quotient. And so on top, we'll simply have dy dt, that is the derivative of my y equals equation with respect to time, over, and on the bottom I'll have my dx dt, that's the derivative of my x equals equation with respect to time. This is one of those situations where, by golly, the differential notation, right, really works out nicely. Look at that. Dy over dx is equivalent to dy dt over dx dt. So this is one of those examples where the notation works out really nicely. Okay, then what's a little bit trickier is because we have that third parameter and we're differentiating with respect to time, if y prime then is my dy dx, right, in order to get my second derivative, if dy dx is also a differentiable function of t, so I've got t's in it, applying the chain rule will then produce our expression for the second derivative of y with respect to x. But because dy dx depends on time, we have an application of the chain rule, which results in the derivative of my y prime expression, that's my dy dx with respect to time, and then over my dx dt, right, with respect to time. So that stays dx dt on the bottom. But I apply the derivative of the dy dx that we did on top. Let's see exactly what this looks like with some parametric equations. Okay, so here we go. We are printable. Let's go ahead and take a look back at our number 2. So which one was our number 2? Our number 2 was our ellipse, where major axis vertical and minor axis horizontal. And let's go ahead and find the slope of the tangent to the parametric curve at t equals 5, 5, or 6. And so very quickly, because we remember our graph from before, we started at 2, 0, and we went around the horn counterclockwise up to 0, 3, negative 2, and down here. And so you can refer to your picture if you like where we had this. And we want to find the slope of the tangent to the parametric curve at 5, 5, or 6. And so as we're spinning here, let's go ahead and just consider where 5, 5, or 6 is. And you can look at your original graph if you like. Or did I give you a new one? Did I give you a new one? Oh, hey, I'm not so bad after all. So at 5, 5, or 6, where would that be? Well, 0, right? And then we did pi over 2, and then we did pi. So 5, pi over 6 would be like right around here, right? Is that where it would be? Well, we have to make sure because our parameter was time, right? It wasn't x, and so we want to make sure that we had. There we go. At pi over negative 2, 0. So yes, 5, 4, 6 is going to correspond nicely to that. So 5, 5, or 6 is going to be right about over in this range. All right. So let's go ahead and find the slope of the tangent to the parametric curve at t equals 5, 5, or 6. In notation, that means we're trying to find the slope of the curve is the same dy dx we had before. Now we'll evaluate at 5, 5, or 6. The difference is to generate our dy dx, we'll differentiate our equation for y and x with respect to time separately. Right? So this becomes dy dt over dx dt evaluated at 5, 5, or 6. So what's the derivative of my y equals equation? Any?
Opposite sign, choose.
Oh, no. Let's do a top first. Sorry, let's do the dy dt.
3 cosine t.
Thank you. So 3 cosine t is dy dt. And go ahead and tell the class dx dt. Right? What's dx dt going to be, Tyler?
Negative 2 sine t.
So negative 2 sine t. Awesome. So we know that our value dy dx at 5, 5, or 6 is simply that expression dy dx evaluated when t equals 5, 5, or 6. So let's see what we get. Ready? Go. I get 3 cosine of 5 pi over 6 is negative root 3 over 2. Yes? Negative root 3 over 2 all over sine of 5 pi over 6 is 1/2 times negative 2 is negative 1. Is that what you guys are getting? So a little reducing, and this actually works out fairly nicely. The negatives will cancel one another out, and it looks like we get 3 root 3 over 2. Now, this is exact, right? But we can get an idea of what this is and then verify numerically with our grapher, but we're going to use our parametric mode. So first, let's get a guess. Recall that root 3 is about 1.7. So we have about 1.5 times 1.7 is about 2.5 maybe, 2.4, 2.5, right? Because 1.5 times 1.5 would be 2.25, and that's about 1.7. So I'm guessing around 2.5-ish. All right, let's go ahead and see now and verify with our calculator. So everybody, we're going to change our mode from our standard function mode to parametric. So everybody, let's go ahead and, oh gosh. I was in advanced algebra in our trigonometry unit where we worked in, oh, the D word, degrees. Yeah, I'm going to fix that right now and put back to radians. We also want our mode to be parametric, not function. So everybody good with parametric? Very good? Okay. So now let's go ahead to our window. We wanted our window to be time values 0 to 2 pi. So we'll go time values 0 to 2 pi. There we are. I was looking. And our x min, we want -3 to 3. Will that work? To match our picture. Oh. And our y values, we did -4 to 4. Just to match our grid. Is that everybody good? All right. So now when we go to our y equals, check it out. When you go to our y equals menu, we've got our parametrically defined curve. So there's my x sub 1t, and that's going to be my 2 cosine t. And now when I hit the variable button, instead of doing our regular plain Jane x, it does t. That's pretty sweet. Our y sub 1 then will be 3 sine t. Huh? Very nice. Okay, so let's go ahead and take a look at our graph and see how we did. Hey, there's our -3 to 3. And you're thinking, that doesn't look the same. It looks like my major axis is horizontally, right? Is that right? Well, what's going on with my picture? Yeah, it's got that rectangular window. I don't like that. I know, I want it to match. I know. So I'm going to do zoom 5 is the z square, and that'll recalibrate it, right, to account for the fact that it's rectangular. Now it matches our picture. Now I'm okay. Right, now I can make it through till lunch for my Oreos, not have to sneak it down in between contact time. Something like that. Cool. All right, so what are we trying to do now? We're trying to verify that our dy dx, our slope of the tangent to the curve at t equals 5 pi over 6 is correct. And so what are we going to do? Well, first I'm going to get an idea of what that is on my regular home screen, just so that I know what we're dealing with. 3 root 3 over 2. Hey, my 2.5-ish was okay. Not so great, but okay. 2.598-ish. Okay, ready? Now's the cool thing. Let's go ahead and go from our graph and do second calculate. And so we're going to use the calculate menu like we did back in the day, back in AB. And we're going to go ahead and check out our menu is different now that we're in parametric mode. It gives us options for dy dx, dy dt, dx dt. Which do we want? We want dy dx. And so I'm going to go ahead and do 2. What time value do I want? 5 pi over 6. Enter. Voila! The cursor jumps on my parametrically defined curve at the point when t equals 5 pi over 6, and it spits out the corresponding slope of the curve, dy dx, which we got as 2.598, corrected 3 places. So that's pretty sweet. So we can verify using our graphing calculator as we did before. So that's pretty cool. Awesome. Could we write an equation of the tangent to the curve at a specified value? Yes. We would just use our x and y equations from the original now. Instead of just finding the y coordinate that corresponds to a given x value, we take our t equals 5 pi over 6, and we get the point x and y to use for my point slope form. And so we're not going to do that, right? You'll do a little bit with vertical versus horizontal tangents in your OTL. But I'm assuming that you guys would be fine writing equation of the tangent line. You just have to get the point of tangency, you've got the slope of the tangent, and then you can write y minus y sub 1 equals m times 20x minus x sub 1. Cool. Questions about that? What else? Well, we could verify the minimum y coordinate attained on the interval 0 to 2 pi analytically. So analytically means we're not doing second calculate max or min with our grapher. We're doing it using our calculus analysis, right? Using optimization or y prime number line or and so on and so forth. So let's go ahead and find the minimum y coordinate attained on the interval 0 to pi analytically. So what are we trying to do? Well, we're trying to minimize y, right? We're trying to minimize y. So if I want to minimize y, I'm going to do the first derivative of y. That would be dy dt in this case, because now we're dealing with a parametric curve. I'll get my critical values of y, right, and then put them on a y prime number line. Or with the closed interval method 0 to 2 pi, I could also do an xy chart. It'll just be a txy chart, right? And I can do it both ways, just so that we can practice. All right, so if I want to minimize y, then I need an expression for y prime. Tyler already told us y prime was, no, Danny told us the y prime was 3 cosine t. Is that right? 3 cosine t? We consider for what values of t on my interval is y prime undefined? Nope. Cosine's good to go for all input values t. So is there ever a place where y prime equals 0? Yes. We've got critical values in this case for y at, bless you, at t equals, well, when is cosine 0 on the interval 0 to pi? Cosine 0 is all my integer multiples of pi over 2. So pi over 2, 3 pi over 2. Because we have a closed interval method, a closed interval, 0 to 2 pi, we could use the closed interval method, right, and compare my output y values, right, and see which is which. I also want to do the number line just so we can practice and verify another method, in case we didn't. So I'll go ahead and make a what? Yes, you guessed it, a y prime number line with my critical values on the interval pi over 2, let's get practice, 3 pi over 2, and from back in the day, a good old sign test. And so we'll go ahead and choose values of t on each of these subintervals and plug them into y prime and see what sign y prime takes on. That'll let me know if my y values are, my y coordinates, I should say, are increasing or decreasing. So here we go. Convenient x value to the left of pi over 2. I'm going to do pi over 4 just so I can practice. So cosine of pi over 4 is positive root 2 over 2 times 3 is still positive. Convenient x value in between pi over 2 and 3 pi over 2 is 3 pi over 4. 3 pi over 4, my cosine values are negative, right? Negative root 2 over 2 times 3 is still negative. Uh-oh. At 3 pi over 2, I have a y prime that equals 0. So then I'm going to go, what do we want here? Maybe 7 pi over 4? You want 7 pi over 4? 7 pi over 4 cosine is positive. All right, so we're looking for the minimum y coordinate attained. By golly, it sure looks like I expect a local minimum of my y values at t equals 3 pi over 2 because y prime changes from negative to positive. Right? A quick verification. And I don't have to do x. I can do a ty chart. What? That's the oddest looking label I've seen for a while. Well, I'm only trying to minimize my y value, so I don't care what the x coordinate is for this particular problem. So what do I put on it? Well, in general, I put my critical values and my endpoints. Well, we already did that before. And at 3 pi over 2, my y coordinate is, sine of 3 pi over 2 is negative 1 times 3 is negative 3. So there's our, it turns out that this y coordinate is both a local minimum and, right, an absolute minimum for my interval 0 to 2 pi. Cool. Are you guys okay if we don't fill in our endpoints of the interval? Old news? Great. All right. Verify the concavity of the parametric curve on 0 to 2 pi analytically. Concavity deals with which derivative? Right? Concavity deals with which derivative? Courtney? the second derivative. So our analysis here, right, is not going to be d2y dt squared. It's going to be back to dy, right, dx. The derivative of that would be d2y dx squared. The second derivative of y with respect to x is going to be concavity of the curve. So we've got to use our new differentiation formula. The derivative of dy dx produces dy prime dt, that's the derivative of dy dx with respect to time, over dx dt again. So let's go ahead and see what that looks like. Ready, go. So we have our dy dx expression. Can we import that? Our dy dx expression is 3 cosine t over negative 2 sine t. Yes, there's our dy dx. So let's get that first. And of course I can't remember that long, so I'm going to just do it again. dy dt is 3 cosine t over negative 2 sine t. Okay. So there's our dy dx. How do I get our second derivative, d2y dx squared? Well, I need to take the derivative of this expression with respect to time and then all over dx dt. So what rule will I use for my top? Well, for my top, put that right there. For my top, I'll use the quotient rule. So the derivative of this y prime with respect to time is a quotient of two functions, both of which depend on t plus t, so I have to use the quotient rule. So for just this top part, I'm using the quotient rule. What? Well, the derivative of a quotient of two functions is, I'm going to just pull the negative out front, right? The derivative of the numerator, 3 cosine t, goes to negative 3 sine t, times the denominator, oh gosh, 2 sine t. Let's see already. Minus the numerator, 3 cosine t, times the derivative of the denominator. 2 sine t differentiates to 2 cosine t. All over the denominator squared is 2 sine of t quantity squared. That in turn is all over dx dt. But dx dt we already have, that's 2 sine t. So we see that's a little bit more complicated, right? Getting to our second derivative of y with respect to x, because each thing is defined with respect to time, right? All right, so can we make this look prettier? Gosh, I sure hope so. So I still have the negative out front. I don't know how that's going to do it first. Can I just distribute it through both on top? Can I just do that one step? So I'm going to erase the negative, because the negative times the negative is a positive all the way through. So I get 6 sine squared t plus 6 cosine squared t. Oh, that's music to my ears. Why am I getting excited about that? Because I'm recognizing that sine squared plus cosine squared is going to reduce nicely. All over 4 sine squared t. That in turn is all over 2 sine t. All right, on top, factorization of a 6 leaves me with sine squared t plus cosine squared t. What's that? Oh, I don't want to steal your puzzle, but I had a hard time containing my enthusiasm. Yes, sine squared t plus cosine squared t is just 1, so factoring out a 6 times the Pythagorean identity of 1, all over, and now I know dividing, right, by 2 sine t is the same as multiplying by the reciprocal. In any case, I'm going to get 8 sine cubed t on the bottom. One more rewrite, you guys, and I think we're done. It looks like 6 over 8 reduces to 3/4, so I'm getting 3 over 4 sine cubed t. For d2y dx squared, my second derivative of y with respect to x. And the reason it was such a mess is because both of my curves were defined with respect to time. Okay, so what do we want? Well, we need our possible points of inflection, right? So are there any values for t for which y dy d2y dx squared is undefined? Yeah, it looks like when sine of t is equal to 0, then I have a 0 on the bottom of a fraction, and that's not okay. So what are my possible point of inflection time values? Well, it looks to me like sine is 0 at 0 and pi, right? And so pi is the only one in the middle of my interval. So t equals 0 and pi, and we're going to make a d2y dx squared number line. And I'm just going to put pi there because 0 and 2 pi are really the endpoints. All right, here we go. Convenient time value between 0 and pi. I'm picking pi over 2. The sine of pi over 2 is positive 1, so I get 3/4 is positive. Uh-oh. That's not good. Thank you, Kobe. Strong work. So back from our original x equals equation for our parametrically defined curve, dx dt is opposite to sine t. So right here, we need negative 2 sine t, which will make this negative for my expression. Therefore, a critical value, right, of pi to the left of would be pi over 2. Sine is 1. So negative 3/4 is negative. Thank you, Kobe. At 3 pi over 2, sine is negative 1 times negative 3/4 is positive 3/4. And now we're expecting our concavity, right, to be concave down on the interval 0 to pi and concave up on the interval from pi to 2 pi because our second derivative of y with respect to x is negative and positive respectively on those intervals. So we've got concave up on pi to 2 pi because the second derivative of y with respect to x is positive, and concave down. Gosh, I'm running out of space here. From 0 to pi, because our second derivative of y with respect to x is negative, and lo and behold, that's what we had, isn't it? We got this concave down, upside down bullshit, concave up, right side up bullshit. So we verified our concavity analytically, still using techniques from AB, but now in the context of parametrically defined curves. Awesome. And that's for you? Ah, that's nice. Our final thing to add with parametric equations is length of a parametrically defined curve. So we're going to go ahead and determine the length now of a curve that has that's been parametrized. And so what can we do here? Well, this first part, I just want you to look and consider, right? If we had some curve right, over an interval, and we considered approximating the length of that curve as you did, right, already back when we were dealing with arc length for equations define y in terms of x, right? What did we do to start that party? Well, we started breaking up this curved path into straight line segments, right? And we got the length of that straight line segment, and then the length of that straight line segment, and then the length of that, and the length of that. how do we find the length of those straight line segments? We're using our old friend, the distance formula, back from geometry, right? Where we just took our y2 minus y1, our change in the y values, and our x2 minus x1, our change in the x values, right? Squared each of those and took the square root, just like the Pythagorean theorem. So to get each of these line segments, what we were really doing was a Pythagorean theorem problem, right? Where we had some change in x was the horizontal distance we scooched over on that subinterval, and we had the vertical leg of my little right triangle was the change in y coordinates, right, on my function, call it delta y, and then we could get our blue line segment value by doing what? Yes, that's right. We took delta x squared plus delta y squared, and then what do we do? Square root of it, baby. There's our Pythagorean theorem. So, if we wanted to then get the length of the entire curve, right, approximated, we'd have to sum up each of those delta L's, right? We have to sum up all those delta L's and get an approximation then for the curve length of that. And as we sum all those delta L's, right, now we're talking about our delta x shrinking to 0, and we're getting the differential dl. So the length of a parametrized curve, right, in the limit would be dl, and we would now replace my delta x, right, with dx squared, and we would replace our delta y in the limit with dy squared. And now what would we do to get an expression for L? Well, we would integrate. So by integrating my dl in the limit, I'm left with big L, the antiderivative of the differential dl, and we're now include our time values and replace our differentials then, right, with respect to time. So we're going to go from where? Well, we'll say the leftmost time value, call it t sub 1, up until the rightmost time value, call it t sub 2 for my interval. The integral of the square root of, and we'll replace my dx with dx dt, the derivative of x, that small change, right, in my x coordinates with respect to time, squared, plus dy dt. My rate of change in the y coordinate with respect to time, squared, close radical, and then with respect to time. My limits are time values, right? My independent variable is time, and so I'll have a dt here, and algebraically we could verify then that dividing each of these by dt inside results in an over dt squared times a dt squared, and then the square root of a dt squared is dt. So just as we generated in our Cartesian arc length formula earlier, we could generate this algebraically as well. But I'm all about the OTL time, baby. So let's go ahead and see if we can't use our arc length formula to answer some questions like, what's the length of the parametric curve on the time interval 0 to 4? All right, so what do we have for this bad boy? Well, this was number 1, so we had -2 comma 0, didn't we? And -1 comma 1, and 0 comma root 2, and 1 comma root 3, and 2 comma 2. And so from our Bellwork, we had this sideways parabola, half of a sideways parabola, and we're going to now get the exact length of this curved path. How will we do it? Easy cheesy, we'll use our arc length formula. So we just generated our arc length formula. L is given by the integral, right, from t sub 1 to t sub 2 of the square root of dx dt quantity squared plus dy dt quantity squared with respect to time outside. So what do we need? Well, we need our expression for dx dt. No problem. That's easy cheesy. What's dx dt? Courtney? Absolutely. So I'll integrate from leftmost time interval 0, rightmost time interval 4, square root of 1 squared, plus, what's dy dt? What's dy dt? Kobe? You can do it with exponents.
1/2 t to the -1/2.
Absolutely. So we've got 1 over 2 root t squared and then dt. Sometimes, right? Sometimes we'll be able to integrate this by hand, but typically not. What I'd like for you to do is be attentive to the gray problems in your OTL assignment versus the ones that aren't shaded. So the gray numbers are going to be like the non-calculator versus the ones that don't have the gray shading. You can use your calculator a lot. So even if we rewrote this once, I don't think it's going to result in a pretty antiderivative. I mean, this is 1 plus, that's 1 over 4t. And while this will make it much easier to punch in, I still think of this as an overall power rule, right? But I don't have the derivative of the quantity 1 plus 1 over 4t there because the t's on the bottom. So what are we going to do? Just math 9 it. Right, let's get a decimal approximation for the arc length of that parametrized curve. On our regular home screen, we'll simply do math 9. Notice how we have t's is going to be, so 0 to 4. Our expression is the square root of 1 plus 1 over parentheses. You need the t to be on bottom, you guys. So if you don't do parentheses, it's going to do 1/4 t. And that's different than 1 over 4t. See what I'm saying? How do you do? Oh my gosh, look at it grind. Worse than homecoming, Tyler. Unbelievable. Let's get an approximation in our head. Well, if this were Pythagorean theorem, we've got triangle would be base 4, height 2. So Pythagorean theorem would give us 2 squared is 4, plus 4 squared is 16 is square root of 20, right? Square root of 20 would be 4 something, and we got 4 something. Hey, cool. Pretty sweet. So that's about 4.647 units. That's pretty sweet. What questions do you guys have about this one? Is yours still grinding?
Yeah, it was.
Oh.
A long time.
And then if you hit something, then you can pause it too. Okay. But you can escape, right, the loop, can't you, by doing power off, second off, or whatever, and it'll jump out of it or whatever. All right, guys, let's close it up. So if x and y are both differentiable functions of t, then what expression gives dy dx in terms of t? What expression gives the second derivative of y with respect to x in terms of t? And lastly, a generalized formula for the arc length of a parametrized curve on the interval t sub 1 to t sub 2. Be ready to share with the class when I call on you. Okay, so what is dy dx in terms of t, Grace?
dy dt over dx dt.
Dy dt over dx dt. Thank you. what's the second derivative of y with respect to x? Right, what will that look like? Vivian?
dy prime over dx.
Awesome. So if we call that y prime, then the second derivative of y with respect to x could be written as dy prime dt over dx dt. Gosh, how did I run out of space so quickly? Where dy prime dt is the derivative of my dy dx expression with respect to time. Ready? And lastly, a general formula for arc length of a parametrized curve. What would that look like? Sophia?
From t sub 1 to t sub 2, the square root of dx dt squared plus dy dt squared.
Awesome. Who got a threefer? Yay! All right, you guys. So we have time. This is great. So I'll go ahead and get your OTL numbers down that I picked out. I did get all odds, so you guys can be checking me in that instant feedback. It looks like numbers 7, 11, 13, 17, 19, 23, 25, 27, and 29. Out of a whopping 9 problems. So not too bad. Awesome. I'll go ahead and stop the recording and update our Moodle.